Hello everyone, hope you are all doing well. Today I am going to explain the topic cubic spline interpolation. This is a topic from computational physics and this is for postgraduate students. Now, what is interpolation? Suppose you are given n plus 1 data points xi, yi. For each value of xi, you have a unique yi where I can take values 0, 1, 2, etc. up to n. That is, starting from x0, y0 to xn, yn, there are n plus 1 data points. In interpolation, we have numerous techniques like Newton's forward difference interpolation, Newton's backward difference interpolation, Lagrangian interpolation, etc. in order to fit an nth degree polynomial which passes through all these data points. Okay, so given n plus 1 data points, we know the techniques to find an nth degree polynomial which passes through all these data points. But here what we are going to do is we will fit a cubic polynomial between each points, that is from x0, y0 to x1, y1 we will fit a cubic polynomial. From x1, y1 to x2, y2 we will fit another cubic polynomial. From x2, y2 to x3, y3 we will fit another cubic polynomial. So in each interval we will fit different cubic polynomials. Okay, and the functions between each successive points is known as spline functions. When they are cubic polynomials, it is known as cubic splines. And the interpolation that done using this method is known as cubic spline interpolation. Okay, so the idea is different cubic polynomials in different intervals. What is the advantage? In the other case, between n plus 1 data points, we are fitting an nth degree polynomial. But here, between n plus 1 data points, we are fitting a smooth curve which is made up of n different cubic polynomials. Okay, n different cubic polynomials. Why we are choosing cubic polynomials? We want to fit a smooth curve. What is the meaning of smooth curve? At each junction, like x1, y1, x2, y2, etc., at each junction, these different splines should be continuous, their first derivatives should be continuous, and their second derivatives should be continuous. Okay, so we are considering such an interpolation for which the junctions are smooth. Okay, so the condition is the splines at each junction should be continuous, their first derivatives should be continuous such that there is no sharp turn, the function should be smooth, and the second derivatives should also be continuous, that is the curvature should also be the same at each junction. In order to satisfy the last condition, second derivatives continuous, we have to consider at least cubic polynomials. Okay, if it is a quadratic one, the second derivative will be constant. Okay, so at the junction, the second derivative of the first spline and second spline will not match. Okay, so we have to consider at least cubic polynomial. That is why this is known as cubic spline interpolation. So the idea is between each data point, we will fit a cubic polynomial. Between x0, y0 and x1, y1, we will fit a polynomial S0, okay, which is called S0. Between x1, y1 and x2, y2, we will fit S1 and so on. So what is the most general form of a cubic polynomial? S0, I can write it as A0 into x minus x0 whole cube plus B0 x minus x0 whole square plus C0 x minus x0 plus D0. The leading term is x cube, then we have terms x square x and a constant term. So this is a cubic polynomial. So this is the general form of a cubic polynomial. So we will define S0 between x0, y0 and x1, y1 as S0 equal to this thing. Similarly, between x1 and x2, we will define a cubic polynomial S1, and that is a1 into x minus x1 whole cube, b1 into x minus x1 whole square plus c1 into x minus x1 plus d1. Okay, so in general, between xi and xi plus 1, the spline function is si equal to ai into x minus xi whole cube plus bi into x minus xi whole square plus ci x minus xi plus di. So the last spline between xn minus 1, yn minus 1 and xn yn, that we will term it as Sn minus 1. Okay, that should be named as Sn minus 1. So the names started with the suffix of the initial point. Okay, so Sn minus 1 is an minus 1 x minus xn minus 1 whole cube plus bn minus 1 x minus xn minus 1 the whole square plus cn minus 1 x minus xn minus 1 plus dn minus 1. So these are the n splines we fitted between the n plus 1 data points. Okay, so we want to find these spline functions. Now, what is the condition? We are looking for an overall smooth curve, that is at the junctions of various splines. The splines itself should be continuous, that is si minus 1 evaluated at xi should be equal to si evaluated at xi. Okay, so si minus 1 is actually the spline between here I made a mistake, this is not S2, this is actually Si. So here between xi yi and xi plus 1 yi plus 1 we have Si, and between xi minus 1 yi minus 1 and xi yi we have Si minus 1. So at the junction xi yi, the splines that meet together is Si minus 1 and Si. So both these splines should have the same value at xi. That is the meaning of this condition. Si minus 1 at xi should be equal to Si at xi. Similarly, Si minus 1 prime, the derivative at xi should be Si prime xi. And the second derivative, Si minus 1 double prime at xi should be equal to Si double prime at xi. And this is the spline Si of x. This is ai x minus xi cube plus bi x minus xi square plus ci x minus xi plus di. We can find the derivative si prime x minus xi whole cube derivative is 3 x minus xi whole square, x minus xi whole square derivative is 2 x minus xi. Here the derivative becomes 1, so it is ci. Second derivative is 6ai into x minus xi plus 2bi. Okay, now using the definition of splines and its derivatives, we are going to substitute in these conditions. So first we will consider Si evaluated at xi as well as xi plus 1. Si evaluated at xi should be yi. Si evaluated at xi plus 1 should be yi plus 1. So put x equal to xi here, you will get di, and that should be equal to yi. That is first condition. Then put x is equal to xi plus 1 here, then you should get yi plus 1. That is the second condition. But here for xi plus 1 minus xi, I substituted as hi. Okay, so xi minus 1 should be hi minus 1 and so on. So the difference between adjacent x values, I denoted it as h. Okay, now the second condition. Second condition is derivative of si minus 1 and the derivative of si should be equal at x equal to xi. So I will I will draw si minus 1 also. This is si minus 1. So this junction should be smooth. Okay, Si minus 1 is between xi minus 1, yi minus 1 and xi yi. The derivative of this curve and this curve at this junction should be equal. That is the second condition. Okay, so if we have Si prime x as this one, I can write Si minus 1 prime x as 3 into ai minus 1 x minus xi minus 1 whole square plus 2bi minus 1 x minus xi minus 1 plus ci minus 1. Okay, when you put x equal to xi in this equation and in this equation, that should match. So that will give me the equation number 6. Ci equal to 3ai minus 1 hi minus 1 square plus 2bi minus 1 hi minus 1 plus ci minus 1. Now, the third condition, that is second derivative. So, take that si double prime at xi, si double prime at xi. Okay, here you have si double prime. When you put x equal to xi, this time will vanish. You will get 2bi. And call it as mi. Okay, what is mi? Second derivative of ith spline at the junction or at the x value xi. Okay, second derivative of ith spline. This is ith spline, and its second derivative at the starting point is denoted as mi. At the starting point is denoted as mi. Similarly, si double prime evaluated at xi plus 1 at the ending point, that is denoted as mi plus 1. Si double prime evaluated at xi plus 1. So you put x as xi plus 1 here, then you will get 6ai hi plus 2bi. So this is equation number 8. So be careful, the definition of mi and mi plus 1 both are second derivative of si. Mi is evaluated at xi, mi plus 1 is evaluated at xi plus 1. Okay, that is the difference. So you have equation 4 to 8, and from equation 7 you can write bi as mi by 2. From equation 8 you can write ai as mi plus 1 minus mi, because this 2bi is mi. Mi plus 1 minus mi divided by 6hi. From equation number 5 you can write substitute for this ai, substitute for this bi. Okay, then you will get ci as yi plus 1 minus yi divided by hi minus 2mi hi plus mi plus 1 hi divided by 6. Just rearrange this, you will get this equation. So this is ci. So we obtained the values of di. Di is yi, and ci is this one, bi is this one, ai is this one. Okay, these are the coefficients we required for writing the spline si. Okay, so these are the values. Similarly, we can write, if you change I to I minus 1, you can write ci minus 1, ai minus 1, bi minus 1 like this. Okay, so you can substitute these values in 6. What is equation number 6? This one. Okay, so you can substitute for ci from here, ai minus 1, ci minus 1, bi minus 1 from here. Then that equation will be like this. Okay, that equation will be like this. If in the above equation, what is the value that I can take? I can take values only up to 1 to n minus 1. I cannot be 0, because if I is 0, that will result in a quantity m minus 1. Okay, m minus 1. Okay, m minus 1 is not defined, because m0 is the starting one. What is m0? m0 is the second derivative of s0 evaluated at y0. m1 is second derivative of s0 evaluated at x1. So m minus 1 is not a defined quantity. Therefore, this I, in this equation, this I can take values from 1 to n minus 1. Why it is n minus 1? Because there is a term mi plus 1. Okay, so when I equal to n minus 1, you will get mn. Okay, if you take I as n, this becomes mn plus 1. That is also not defined. That is also not defined. Okay, so this is the expression. We can simplify this expression. We can simplify this expression. You take mi minus 1, mi plus 1 to the left hand side. Then mi minus 1 into, what are the terms containing mi minus 1? Group all those terms. Mi, group all the coefficients. Mi plus 1, group all the coefficients. Right hand side is this term is there and this term is there. Okay, so those two terms. Then solving, finally you will get hi minus 1 mi minus 1 plus 2 into hi plus hi minus 1 into mi plus hi mi plus 1 equal to 6 into this quantity. Okay. If you put I equal to 1 in this expression, you will get h0 m0 plus 2 into h0 plus h1 m1 plus h1 m2 equal to 6 into y2 minus y1 by h1 minus y1 minus y0 by h0. When you put I equal to 2, you will get h1 m1 plus 2 into h1 plus h2 m2 plus h2 m3 equal to 6 into y3 minus y2 by h2 minus y2 minus y1 by h1 and so on. When you put I equal to n minus 1, you will get the last expression. So how many equations are there? Starting from I equal to 1 to I equal to n minus 1, there are n minus 1 equations. And what are the unknowns? h0, h1 are all known. y2, y1, yn, yn up to yn, the values are known because the data points are already given. Okay, so y1, y2 up to yn are known. h1, h0 are known. The unknowns are m0, m1, m2, etc. mn. What are these m0 to mn? They are actually the second derivatives at each of these points. m0 is second derivative of s0 at the starting point. m1 is second derivative of s0 at the ending point, and it is same as the starting of the second derivative of s1 at the starting point. Both are the same, okay, because they are continuous. Similarly, mn is the second derivative of Sn minus 1 at xn. So these are not known initially because we doesn't know the equation for these splines. So these second derivatives are also unknown. How many unknowns are there? Starting from m0 to mn. There are n plus 1 unknowns. There are n plus 1 unknowns starting from n plus 1 unknowns starting from 0 to n. There are only n minus 1 equations and we have n plus 1 unknowns. So not possible to solve uniquely. Okay, there is no unique solution. We need two more conditions. We need two more equations. And then only we can solve for these n plus 1 unknowns. Okay. And there are many ways in which these two extra conditions are specified. Okay, there are many methods in literature, but I will discuss only two methods. The first one is known as natural spline. Natural spline. Here, what we are going to do is, we will just put m0 and mn as 0. m0 is, I already mentioned, it is the second derivative of s0 evaluated at x0, and you take it as 0. And second derivative of Sn minus 1 evaluated at xn, that also is 0. Okay, suppose you fixed those two values as 0. Then what will be this first equation? This term vanishes and you will get the remaining. 2 into h0 plus h1 m1 plus h1 m2 equal to 6 into this one. Similar, second, third, fourth equations are all remains the same. Last equation, this mn will vanish. So that equation will be like this. Then, now we have n minus 1 equations because all the equations are there. Okay, the only difference is in the first equation one time vanished and the last equation one time vanished. So the number of equations are still n minus 1, but the number of unknowns are now only from m1 to mn minus 1. So equations, number of equations and number of unknowns are same. You can write it in a matrix form. The first equation is 2 into h0 plus h1. m1. Okay, so you can write it as 2h0 plus h1 into m1, h1 into m2 in a matrix form. Okay, so this is a square matrix of order n minus 1, n minus 1, n minus 1, n minus 1 order square matrix, and this is a column matrix of order n minus 1 into 1. Okay, and this is again a column matrix of order n minus 1 into 1. So this is a set of linear equations. You can solve for it to find m1, m2, etc., mn minus 1. Once we solved for m1, m2, etc., mn minus 1, we already have values for m0 and mn. So we have all the values from m0 to mn. Using these m values and the given data points, we can find ai, bi, ci, di. Using these values of ai, bi, ci, and di, we can find the spline. Si of x is equal to ai x minus xi cube plus bi x minus xi square plus ci x minus xi plus di. Okay, so I will give you one example. Find natural spline for the following data. X, y. X values are 2, 3, 4. Y values are 11, 49, 123. Okay. So I can say x0 is equal to 2, y0, x1 equal to 3, x2 equal to 4, y0 equal to 11, y1 equal to 49, y2 equal to 123. h0 is 1, h1 is 1. What is h0? It is, h0 is by definition, h0 is x1 minus x0. h1 is x2 minus x1. So they are respectively 1. m0 and m2 are 0 in natural spline. Okay, in the case of natural spline, m0 and mn are 0. Here mn, there are only 3 data points. So n is 2, 0, 1, 2. So m0, 0, m2, 0. The only unknown is m1. What is m1? From this equation, we have 2 into h0 plus h1 into m1 equal to 6 into, here I forgot to write as 6 into y2 minus y1. So that is why 6 into y2 minus y1 by h1 minus y1 minus y0 by h0. h0 and h1 are 1, so it becomes 4 1, m1 equal to 6 into y2 minus y1. It is 74, y1 minus y0 is 38. Okay, just take the difference of these values. So you will get m1 as 54. So y0 11, y1 49, y2 123, m0 0, m1 54, m2 0, h0 1, h1 1. You can calculate a0. a0 is m1 minus m0 by 6h0, it is 9. b0, it is m0 by 2, it is 0. c0, it is y1 minus y0 by h0 minus 2 m0 h0 plus h0 m1 by 6. And that if you calculate, you will get 38 minus 9, it is 29. d0, it is exactly equal to y0, it is 11. Similarly, for the second spline, you can calculate a1, b1, c1, d1. The values are respectively minus 9, 27, 56, 49. You can easily verify by putting these values here. Okay. So what is S0 of x? S0 of x is a0 x minus x0 cube plus b0 x minus x0 square plus c0 x minus x0 plus d0. Substitute for a0, b0, c0 and d0. And by applying the equation for a minus b whole cube as a cube minus 3a square b plus 3ab square minus b cube, you will get this thing. And the final expression is S0 of x equal to 9x cube minus 54x square plus 137x minus 119. This is the spline between the points 211 and 349. So you have to verify it by putting x equal to 2. You will get 11. If you put x equal to 3, you will get 49. So this is the spline between the points 211 and 349. Okay. Now you can calculate the derivative S0 prime x. It is 27x square minus 108x plus 137. S0 double prime x, it is 54x minus 108. I already mentioned that m0 is the second derivative of s0 evaluated at x0, and m1 is the second derivative of s0 evaluated at x1. So second derivative of s0 is here. If you put x equal to x0, that is 2, you will get m0. Okay, we already took m0 as 0. Okay, so here from this spline also you should get the same answer. What is m1? Take the second derivative of this value at x equal to 3. Then you will get 54. Okay, so everything is matching. Now we will calculate S1 of x. It is A1 is minus 9, B1 is 27, C1 is 56, D1 is 49. Substituting and solving, you will get minus 9x cube plus 108x square minus 349x plus 367. So S1x is the spline between 349 and 4123. So if you put 3, you should get 49. If you put 4, you should get 123. So that is also correct. What is S1 prime x? You take the derivative of S1 of x, then you will get this one. S1 double prime x is this one. If you put x is equal to 3, you will get 54. If you put x equal to 4, you will get 0. Also, we can verify one more thing. S0 prime evaluated at 3 should be equal to S1 prime evaluated at 3. Okay, S1 prime evaluated at 3 is minus 27 into 9 plus 216 into 3 minus 349. What is this value? 7 into 9, 63. So it is minus 243 plus 648 minus 349. Okay, what is this value? 500, 580, 592, 592, 648. It is 56. Okay, now what is S0 prime 3? What is S0 prime? 27x square minus 108x plus 137. 27x square minus 108x plus 137. So it is 243 minus 324 plus 137. So it becomes 300 and 380 minus 324. 380 minus 324 is again 56. So 56 equal to 56. The first derivatives at the junction should be the same. Okay, so all the conditions are satisfied by these two splines. Now I will plot these splines. Okay, and this plot is the x value is from 2 to 4. The x-axis is from 2 to 4. This red curve is S0 of x, and this yellow curve is S1 of x. What is the meaning of cubic spline interpolation? You have 3 data points. The first one is this one, and the second one is 3. X value is 3. Okay, somewhere here. So between 2 and 3, you have to fit S0. Between 3 and 4, you have to fit S1. Okay, you are not going to fit a single polynomial in the entire range. Between x0, that is here 2, and x1, that is here 3. Between 2 and 3, you are going to fit this red curve. And between 3 and 4, you are going to fit this yellow curve. But both the curve have the same value, have the same derivative, have the same second derivative at this junction. Okay, so if you plot just red curve between 2 and 3 and yellow curve between 3 and 4, it will be a continuous one. Even though they have different equations at the junction, it will be smooth. Okay, I think it is clear. Now we will consider the second case, clamped cubic spline. Okay, so our problem was we have only n minus 1 equations and n plus 1 unknowns. So we have to express any of the m values in terms of other. Okay, in the natural spline case, we fixed m0 and mn as 0. But in the clamped cubic spline case, we have two conditions. Okay, that is the value of first derivatives at the two ends. The first end is of spline S0. So the first derivative of S0 prime evaluated at x0, that is the starting end. That should be A. And the last spline is Sn minus 1. Its derivative evaluated at the final point Xn, that is B. These are the given conditions. Okay. So we have the splines S0 and Sn minus 1. These are the first spline and last spline. The derivative of first spline at the starting point, derivative of last spline at the ending point are given respectively as A and B. Then how can we find the splines? Okay, that is known as clamped cubic spline. So what is S0 prime x? It is 3a0 into x minus x0 square plus 2b0 into x minus x0 plus c0. If you put x0 here, you will get c0. So c0 is a. c0 is by definition it is y1 minus y0 by h0 minus 2 h0 m0 plus h0 m1 divided by 6 equal to a. Rearranging this, you will get 2 m0 plus m1 equal to 6 by h0 y1 minus y0 by h minus a. So this is a condition between the different m values. So we got one condition. Then the final spline Sn minus 1 x, that is an minus 1 x into x minus xn minus 1 q plus etc. Okay, then take derivative, then put x equal to xn. You will get 3 an minus 1 hn minus 1 square plus 2bn minus 1 hn minus 1 plus cn minus 1. This value is actually b. Okay, so you substitute for an minus 1, bn minus 1 and cn minus 1, and rearranging you will get a relation connecting mn minus 1 and mn. Mn minus 1 plus 2mn equal to 6 divided by hn minus 1 into b minus yn minus 1 divided by hn minus 1. So in the n minus 1 equations that we already have, that is these equations. These are the n minus 1 equations. Here you can eliminate m0 using the relation connecting m0 and m1 that we obtained there. And you can eliminate mn using the relation connecting mn minus 1 and mn we obtained in clamped cubic spline case. Okay, so this h0 m0 term you can substitute for m0 from this value, from this condition. Okay, substitute for m0. Then you will get this condition, and rearranging you will get 3 by 2 h0 plus 2 h1 into m1 plus h1 m2 equal to 6 into y2 minus y1 by h1 minus 9 y1 minus y0 by h0 plus 3a. Similarly, in the last equation for mn, you can substitute from this equation mn. Then you will get finally this equation hn minus 2 mn minus 2 plus 2 into hn minus 2 plus 3 by 2 hn minus 1 into mn minus 1 equal to 9 yn minus 1 by hn minus 1 minus 6 yn minus 1 minus yn minus 2 by hn minus 2 minus 3b. Okay, all the steps are written here. You can just verify. So the first equation changed to this one, last equation changed to this one. All the other equation remains the same. Now you have n minus 1 equations and n minus 1 unknowns starting from m1 to mn minus 1. Okay, so you can solve and find the values of m1 to mn minus 1. Once we have m1, you can find m0 using this equation, and once you have mn minus 1, you can calculate mn using this equation. So we will get all the n plus 1 m values. So I will do the same example. Find clamped cubic spline for the following data. Data is the same as before, 2, 3, 4, x values, y values 11, 49 and 123. The derivatives at the first end is 7 and for the second spline the derivative as last point is 25. These are the given conditions. So A is 7, B is 25. These are the x0, x1, x2 values, y0, y1, y2 values, h0 is 1, h1 is 1. All these are same as in the previous case. So the first equation, you can substitute the values and you will get 7 by 2 m1 plus m2 is equal to 123. And the relation between m0 and m1 becomes 2m0 plus m1 equal to 186. And the last equation, mn minus 1 plus 2mn, that equation will give you m1 plus 2m2 equal to minus 294. Okay, so you can write this equation 7 by 2 m1, that is here. So that becomes 7 m1 plus 2m2 equal to 246. Using these two relations, you can eliminate m2 and 6m1 is equal to 540, m1 is equal to 90. Put this value of m1 here, you will get m2. Okay, m2 is 190 minus 192, and using this value of m1 in this expression, you can get m0. So m1 is 90, m2 is minus 192, m0 is 48. Once we have the value of m0, m1, m2, h0, h1 are already given. Okay, so in the clamped cubic spline case also, you can find A0, B0, C0, D0, A1, B1, C1, D1. Okay, you can verify these values just by simply substituting in this equation. Okay, in the natural spline case, m0 and m2 we took it as 0, but here we have m0 as 48 and m2 as minus 192. Then we got A0 as 7, B0 24, C0 7, D0 11. So the S0x spline is 7x cube minus 18x square minus 5x plus 37. If we evaluate this at 2, we should get 11. If we evaluated at this at 3, we should get 49. And its derivative S0 prime x is 21x square minus 36x minus 5. If we evaluated this derivative as the starting point, you should get the given condition A, value of A, it is 7. Similarly, the second spline A1, B1, C1, D1 are given. So substituting in this, you will get S1 of x equal to minus 47x cube plus 468x square minus 1463x plus 1495. When you put x equal to 3, you will get 49. When you put x equal to 4, you will get 123. Again, the derivative evaluated at 4 will be 25. So all the conditions are correct. So these are the correct equation for spline S0 and S1. And if you plot S0 and S1 between 2 and 4, this red curve is S0 and this yellow curve is S1. Okay. Now I made a mistake. This yellow curve is actually this yellow curve is S0. This is a mistake. This is S0. This is S1. The equations I have to change. S0 is 7x cube minus 18x square minus 5x plus 37. Okay, so this yellow curve is S0 and this red curve is S1, and its equation is I think minus 47x cube, 468x square minus 1463x plus 1495. Okay, so between 2 and 3 you have to take this yellow curve. Between 3 and 4 you have to take this red curve. Okay, that is the cubic spline idea. Between a pair of points 2 11 and 349 you have to consider this yellow curve, and between 349 and 4123 you have this red curve. Okay, so both are represented by different curves, and at the junction these two curves have the same value, first derivative, second derivative. So this is the idea of splines. Okay, so fit different cubic polynomials in different intervals such that overall you will get a smooth curve. Okay, thank you.